Hello students, today we are going to start a new chapter. This chapter number 6, and this is about control system analysis and design by root locus method. So root locus method. Now root locus we have to understand. Okay, so let's talk about the motivation, what it is. As you know, this course is about vibrations and control, so we are into control system now. Analysis and design. Analysis part, basically making sure or finding out whether the system is stable or not. Yeah, so this is analysis. Design, choosing some parameters such that system performs in the desired way. Yeah, so this is the inverse method. Yeah, so by analysis we will find out whether system is performing in the right way or not, whether system is stable or not. Design means in order to make system stable, what should be the parameters, right? So that's what the meaning of that by root locus method. So we will understand today root locus. What is root locus? Okay. Now we have been studying a few things like control system. The feedback control system, as we have seen, could be something like, say, this is GS. Yeah, this is general the block diagram, and it may have a feedback gain as well, or feedback transfer function. So we have here negative feedback, yeah, so minus this plus. Here we have reference, say RT, and then here CT. Yeah, or we can, instead of taking, since this is all in S domain, we can also write here RS, here this is CS. Okay, so since everything is in terms of S, we write like that. So this we have been studying, yeah, and open loop, we know that open loop transfer function is equal to GS times HS, and closed loop transfer function we have been writing as TX is equal to GS divided by 1 plus HS times GS. So this we have been writing this way. We know how it comes and all. For us it's given now. Now the thing is, we have to analyze it. Analyze is for what? Analyze, there may be some parameter, yeah, and for that we have to analyze how it behaves, how to choose the parameter, or how to choose the parameter is design part. Analysis part, if this parameter is this much, then determining the performance, for example stability will be one of, or the error, steady state error. We will take on one example. So best way to take example from simple to difficult one and see what we gain out of it. Yeah, so take example number 1, and where we are taking it as GS equal to, simplest one, let's call it K is our parameter given. Here we have S plus 1. GS is a first order system, yeah, which we have some GS. This we can also visualize as there is a proportional controller here, K, and then here we have first order system 1 over S plus 1, and here we have unit minus plus. Here we have unit feedback loop like this. Yeah, and in that case the value, the GS will be equal, we combine them together, so it becomes K over S plus 1, right? So we are writing like this one, but when we combine, we get the combined GS will be K over S plus 1. Yeah, so this is one example. Okay, and a closed loop TS will be given by K over S plus 1 divided by 1 plus HS, in this case 1, so we get 1 multiplied by this only, so K over S plus 1. Okay, now what is the question? Okay, so the question is how K, value of K is going to change the behavior. Yeah, and how do we know the behavior? If we know where the root is, yeah, on the S plane. Yeah, this is the S plane as we have seen. This is I omega, and here sigma, where S equal to sigma plus I omega, right? So S is in S domain. The S is a complex, sigma is a real number, omega is also real number, I omega is complex. So we plot it here. We know that as long as this is this side, we know that this is going to be stable. Also, we can find out not only a stable, but how it is going to behave. For example, if it is a second order system, we can find out whether it will be overdamped or underdamped and critically damped. All those things we can find out just looking at the root. Yeah. Okay, so here the idea is to vary K and find out the root. So root locus is nothing but, root locus, what is that? Root locus is plot of the roots, yeah, plot of roots as a function of K. Yeah, plot of roots as a function of K on S plane itself, on S plane. Okay, here only I'm going to vary K and see how the root is following a path. Okay? So plot of root, so and or the locus of root, right? Or the locus of root, and hence the root locus. There is one variable. In this case, what you say is K here, right? So K, we are going to change the K, and accordingly we will find out. What we see here, if you simplify, we get K divided by, we get S plus 1 plus K, right? This is our TS. Now, we know that if K equal to 0, what is the characteristic equation? Yeah, so we can write this is nothing but PS over QS form, and characteristic equation in this case is QS equal to 0 or S plus 1 plus K equal to 0, and what we know here is S equal to minus 1 minus K. And how to plot this one? Put K equal to 0, S equal to minus 1. So we start from here. We make a cross here. Cross means it is the pole. Pole of what? Pole of a open loop system, right? So here, right now, either this is you call it a pole. Pole means the, you can also say the this one is the root. This one root when K equal to 0. Either you can do like that, or you can say for open loop, look at this one. So this one is open loop. This is open loop system. For open loop system, where is the pole? Where is the root of the characteristic equation? S equal to minus 1. So this is pole. You can say that pole of the open loop system. Right? Pole of the open loop system, because this is open loop, right? So in this case, what do you guess? Even like open loop is not just GS, but GS times HS, this one. Yeah, so which is equal to, in this case, that one. Okay, so let me erase it and then we'll explain. Okay, so far what we got? We got open loop transfer function. Okay, let's call it TO, right? TOS. For us is a K over S plus 1. Yeah. The present example, closed loop transfer function, yeah, TS, yeah, is equal to K over S plus 1, yeah, and 1 plus Ks plus 1. For us, this is what we have, S plus 1 plus K. Now, I'm going to give reference to both of them, open loop transfer function, also closed loop transfer function as well. So be careful, give attention here. If we see the pole, whenever we say pole, means the root of corresponding characteristic equation, that is denominator equal to 0, right? So closed loop transfer function we have been writing in terms of PS over QS. What is the idea? Here idea is if K varies, how does the root of closed loop transfer function varies? Yeah. So this is the question that the root locus is going to answer. Okay. And here, in order to know this, we don't have to actually find out what is the closed loop transfer function. That can be based, if you know the open loop transfer function, you can do it. Because in denominator, you have 1 plus closed loop open loop transfer function only, right? So you can have the full form of this, from there also you can do it, or if you just know the open loop transfer function, that also may be sufficient of doing it. Okay. So anyway, our characteristic equation, if you just look at this one, the QS equal to 0, and that tells me S plus 1 plus K equal to 0, and we know that S equal to minus 1 minus K, and if you want to plot it here, we have sigma, we have I omega, and we know that if K equal to 0, we have S equal to minus 1 here, right? Let's make it cross. This corresponds to K equal to 0. Now you increase K. Let us say K equal to 1 now. Yeah? K equal to 1. Now we are assuming K is positive. Whenever you are plotting this, you will assume K is positive. So in this case, the K, increase it. K equal to minus 1. So K equal to 1. So this is the point, right? So at this will be K equal to minus plus 1. And so on. You will find that this will move this way. It will start at s equal to -1 and it will go toward infinity. When k equal to infinity, s is also minus infinity. Yeah, so go here s equal to minus infinity, which corresponds to k equal to infinity. So this, whatever we have drawn, this one is nothing but what is known as root locus. So this is the root locus. Okay, although this is for a very simple problem, we have taken just one first order system in which we have like this one. Okay, although we have drawn this one k equal to 0 and we have put a cross here, either you can call it this, all these are roots of a closed loop system. So you can say here root locus of closed loop system, right? Closed loop system. We are drawing this for closed loop. However, just looking at the open loop system s plus 1, the pole of the open loop system is at this one. This cross, this point is also the pole of the open loop system. Meaning that our root locus starts from the pole of the open loop system. That's what I wanted to stress. Okay, just looking at the open loop system, you can find out where the root locus starts. Yeah, so root locus will start from the poles of the open loop system. This was a very simple example. Now we will add a few more things and see how it goes. Let's now have a system something like k, okay, s plus 2 divided by s plus 1. This is our open loop transfer function. Yeah, and hence the closed loop will be equal to k s plus 2 divided by s plus 1, 1 plus, here we don't know, this is the open loop transfer function, so here unless we know what exactly the configuration is, we cannot find out. So let's we just say question mark here. What we know here is t naught s will be there. Okay, here this is for the feed forward transfer function divided by 1 over the open loop transfer function comes here. So here we don't know what is the feed forward transfer function. It could be this divided by something. Yeah, so we don't know, but closed loop transfer function will look like this one. Yeah, and hence the characteristic equation, this will be Ps over Qs. Yeah, and the characteristic equation, even if we don't know what it should be here, but we know the open loop transfer function looks like this one, we know that the characteristic equation in this case, this will be a ratio. Okay, this will be something like this one, but still we can write the whole thing has to be 0, right? So so characteristic equation, you can write this characteristic equation will still be 1 over 1 plus Ts equal to 0. We can still write that. Yeah, although T naught S is in form of ratio, but once we do, right, so we write like this one, 1 plus K S plus 2 over S plus 1 is equal to S plus 1 plus K S plus 2 S plus 1 is equal to 0. And finally, from here, characteristic equation comes back to S plus 1 plus K S plus 2 equal to 0. Mind it, this S plus 1 will automatically, this will be cancelled from the numerator part. You know, so hence we end up with this one, meaning that if we know the open loop transfer function, from there also you should be able to find out the closed loop, the characteristic equation of the closed loop transfer function, and which is like this one. Now the idea is to plot this. Yeah, plot this. Why? Because it will give us idea how the pole of the closed loop transfer function changes. Yeah, so this we can write it like here. We have k, right? K plus, this is k plus 1 times s plus, right? And then we have 2k plus 1, yeah, equal to 0, and hence s equal to minus 2k plus 1 divided by k plus 1. So this is what the root is, and if you want to plot it, how will you plot? Remember, we start with 0, k equal to 0. So k equal to 0 will be equal to minus s equal to minus 1, right? Okay, now s equal to minus 1 is coming again, and this is again, this actually corresponds to the pole of the open loop system, open loop transfer function. Okay, k equal to 0 corresponds to the open loop transfer function, and you have s equal to minus 1. Let's plot it here. So we have sigma pi omega. What do you get? You get s equal to minus 1. So here we cross it, we say minus 1. Yeah. Okay, now you increase k now. Okay, and what is the maximum value? The maximum means magnitude wise, I'm asking. So if k equal to infinity, then what is the value? So k equal to infinity, k tends to infinity, then s equal to, we can write minus, we have to take the limits, right? S equal to limit k tends to infinity, and we have minus, we divide by k, so you have 2 plus 1 over k, then 1 plus 1 over k, k tends to infinity, and hence you get minus 2. What is minus 2? Minus 2 is the, look at here, s equal to minus 2, s plus 2 is in the numerator. Yeah, so what we see here is like this one. Yeah, so s equal to minus 2 is basically, this is the 0 of the 0 means for this is the numerator part, right? The 0 of the numerator of the open loop transfer function. Yeah, and this is here, 0 is denoted like this one. Okay, 0 is denoted as the 0 here. This point, what we see, s equal to minus 1, s equal to minus 2, s equal to minus 1 here, s equal to minus 2. This cross, which is pole, corresponds to k equal to 0, and this is k equal to infinity. And the values moves like this. It goes from here. So what you see here, if you have intermediate value, let us say we have 2, right? So you can check it. Okay, k equal to 2 now. Okay, so s equal to minus 2 times 2 plus 1, and then 2 plus 1. Okay, right? And what do you get? We get minus, then 4 plus 1, 5 by 3. Yeah, so we get 1 minus 1 point some value. Okay, so that means it will be somewhere here, and so on. If you increase, keep on increasing, you will move this way, and very slow moving, and k equal to infinity, you have this point. So actually the value of k, if you increase the k value will increase from 0 to infinity, and it will lie between this and this. What it tells you is the root of the characteristic equation for the closed loop transfer function will be confined within s equal to -1 to s equal to -2 only, regardless of what value of k you are taking. That's what it is telling you. And that's why this root locus, this is what the root locus you have plotted. Yeah, and this is a powerful way. Just looking at the plot, you get to know lot of information about it. Yeah. So what we learned so far, we learned that the open loop transfer function is important. This gives you clue. What clue it is giving you? It gives you, if you know the pole is denominator. If you make denominator equal to 0, now whatever the root you get, you denote it like a cross, you put the cross there. Okay, so that is the poles of the open loop transfer function. Then numerator, you make it equal to 0. Whatever the value of s you get, you call 0 of the open loop transfer function. You denote it like 0 here. Now value of k equal to 0 corresponds to this cross. K equal to infinity corresponds to this 0. We have seen that the root locus, that is the plot of s, yeah, from k equal to 0 to k infinity will be like this. Means it will start at a cross and end at 0. Yeah, so that's what we have seen. It will start from a cross, ends at a 0. We will see more example, more complex we will put, and that way. So everywhere, just give attention to what we have learned so far will be reflected again and again. Let's make it more complicated. Okay, so we will add s plus 3 now here. Okay, okay, k, s plus 2, s plus 1, s minus 3. Yeah, so we can, straight away we can write here poles. S plus 1, s plus 3 equal to 0. Yeah, okay, for the open loop transfer function, we have the poles s plus 1 times s plus 3 equal to 0, and hence we have s equal to -1 and -3. Okay, now zeros is s plus 2 equal to 0, s plus 2 equal to 0, and hence s equal to -2. Yeah, we got that. If you already know about root locus, and after you learn this chapter, you will immediately, you can, based on this, you can plot immediately. Okay, and how will you plot? You will do like this. Okay, so s plane sigma I omega. Poles you will denote it as cross. So this is -1. Okay, and this one, okay, -1, and another here is -3 here. So both are cross. Okay, poles basically. Yeah, so this is cross, and the zeros is 0. S equal to -1, so 0 is here, -2. Now somebody asks you, or you have to now figure out that how is the root locus? Yeah, okay. If you know the root locus, you have learned about it, you can tell that this will be from here to here, and then there will be nothing here, and then from here it will start this way. So the root locus is this, okay, from here to here, and then from here to here, like this. Okay, so this corresponds to k equal to 0. This also corresponds to k equal to 0. This corresponds to k equal to infinity. At infinity also, right? This is minus infinity, and at infinity also the k corresponds to infinity. So from 0 to infinity, why it happened? Because we have got 2 poles and only 1 0. So from here it will start, it will end here. As we talked earlier, the root locus will start from the pole, will end at 0. But again, when you have 2 roots, when you have 2 poles, then the second pole will not go to backward. Yeah, okay, it's not that always it has to go left side only. It's not like that. Okay, but here there are many other things. Okay, so just there will be, it has to go to infinity. It has to go to infinity because of some reasons. One thing will be to see, just directly we solve this one and we try to find out whether really it goes or not. Okay, and then we will look at why, in general, how will we decide whether it goes to the right or it goes to the left. Okay, so we will find out. So let's write down the characteristic equation for the closed loop system, and which is 1 plus T naught S is equal to 0, and which comes to be 1 plus K S plus 2 divided by S plus 1 S plus 3 is equal to 0, and this gives us S plus 1 S plus 3 plus K S plus 2 equal to 0. So this is the equation. Okay, now let's put k equal to 0 here. Okay, so k equal to 0. Put it here. So k equal to 0. So this is out. So we have S plus 1, S plus 3 equal to 0, and that gives us S equal to minus 1 and minus 3. Now k tends to infinity, and then what happens? K tends to infinity. In that case, divide by k now. So we get 1 over k S plus 1 S plus 3. Yeah, and plus here we have S plus 2, right, is equal to 0. So when k tends to infinity, we have what we get? We get S plus 2 equal to 0, and hence S equal to minus 2. What about this one? Okay, so this we could not capture here because we have numerator denominator both basically, so somewhere it is going to reflect. In that case, we are going to extend it, the whole of it. So we just write S plus 1 times S plus 3 plus K S plus 2 equal to 0. So S equal to minus 2 corresponds to k equal to infinity. So we are writing k equal to infinity. These two are at k equal to 0, minus 3 and minus 1. So that I'm indicating. We have to find out this one. So we have like this. So we have S square plus 4S plus 3 plus ks plus 2k, yeah, equal to 0, and here you get S square plus 4 plus ks plus 3 plus 2k is equal to 0, and from here you can find out S equal to minus 4 plus k, yeah, Okay. S equal to minus 4 plus k s minus b plus minus root b square, so 4 plus k square minus 4 ac, so 3 plus 2k and root divided by 2. Okay, we can further, so here we have root, and this is 16 plus 8k plus k square minus 12 minus 8k over 2. So we get from here, sorry, the minus 4 k is like this one, so we get minus 2 plus k over 2 plus minus, and here we get half root. Okay, and this is 16 k square 8k, so we get k square plus 16 minus 12 4. So we get like this. Yeah. Okay. So what we see from here, that one of the roots at least will be infinity if we k to infinity. So if put k equal to infinity, so k equal to infinity here, so this becomes minus, you take the minus part here, and this also infinity, so infinity minus infinity is infinity. So one of, in fact both of them, okay, so will okay, so this one we can also write it as equal to minus 2. So let me write here this side. S equal to minus 2 plus k over 2 plus minus root, taking inside the root, so it becomes 4, so k over 2 square plus 1. That's what we get. Yeah. Okay. Okay. So one of them, this, yeah, so here it's minus, here is minus, k tends to infinity, k tends to infinity. So one of them, one of the roots will be infinity. So S equal to infinity if k tends to infinity. One of them will be there. The other may not be, okay, and other should not, but we already found out the other value, that is S becomes minus 2 when k equal to infinity. Yeah, so that really means one of the roots is in infinity. Yeah, so hence what we see it here. Okay, so what we have seen here is it goes from, so if all the roots are on the real axis, then it will start from the first the pole, yeah, first pole. From first pole you go to the 0, from the second pole you go to the second 0. If there is no 0, it will go to infinity. This also because of many things. Yeah, many things, as I said earlier, that we have to look at from different perspectives. Yeah, so we will take one more example which will be based on the complex number, a complex root, and we will see how to work out, and then we will go to the general strategy you need to plot the root locus. Let's look at open loop transfer function T naught S is equal to K over S square plus 1. Okay. Okay. And hence the zeros, in this case there is no zeros, only the poles. This open loop, remember? Okay. Equal to HS times GS as we discussed earlier. So poles will be S square plus 1 equal to 0, and hence poles means cross. S equal to plus minus I. So if you look at this one, sigma I omega, and we get I here, we get minus I here, and here these crosses are. Yeah, so these are the poles will be here. Now, which direction should they proceed? Okay, now characteristic equation, we can find out characteristic equation, and what is that? 1 plus T naught S equal to 0. 1 plus the open loop transfer function equal to 0. Yeah, and that really means 1 plus K over S square plus 1 equal to 0, and hence we get S square plus 1 plus K equal to 0, and S equal to what we get? Minus K minus 1 root, and hence it will be plus minus, here we write S equal to plus minus like this. So S equal to plus minus I root K plus 1. Okay, and K equal to 0 means S equal to plus minus I. K equal to infinity means S equal to nothing but plus minus I infinity, right? Put infinity here. So what happens? This is going to move this way. It will go from start from here, cross, go upward like this. Okay. So in other words, this is going to start from this, cross, it will move like this one, start from here, move this way. Yeah. Okay. So this was the root locus for this open loop transfer function. Okay, let's take another example. So open loop transfer function Ts equal to, let's K over S plus 1 times S plus 3. Yeah. So in this case, earlier we had taken an example where we have S plus 2 here, so I'm not taking that. So we have S plus 1 and S plus 3 only. That's it. Means there is no zeros. Okay. Then what happens? So characteristic equation will be 1 plus T naught S equal to 0, where K is variable, a design variable that we have to find out or analyze, and hence we have simply it will be S plus 1 multiplied by S plus 3 plus K equal to 0, or S square. Here we can find out when K equal to 0, when K or simply from here we can find out the poles. Yeah, or simply write here poles, that is cross S plus 1, S plus 3 equal to 0, and hence S equal to minus 1 and minus 3. Either you can write like this one or put K equal to 0 here and then solve it. This is the same thing. Okay, no zeros here. So how do you plot? We are going to write like this one. Hence the one cross will be here minus 1 and the another cross minus 3. Now the question is which way it goes. It goes this way, what? That we have to find out. Okay. Now here this equation, let's do it the slow way of doing it. So we can write as S square plus 4 s plus 3 plus k equal to 0. Yeah, and then s equal to minus b plus minus root square b square root b square minus 4 3 plus k by 2 is equal to minus 4 plus minus root 16 minus 12 minus 4k. Yeah, divided by 2 which is equal to minus 4 plus minus root 4 minus 4k divided by 2 is equal to minus 4 plus minus 2 root 1 minus k by 2 is equal to minus 2 plus minus root 1 minus k. So this we get. Okay. So k equal to 0, we have minus 2 and minus 3. When k equal to infinity, what do we get? We can put k equal to infinity here and see what happens. So k equal to infinity, or k tends to infinity, and s equal to minus 2 plus minus root 1 minus infinity, and hence what we will see is we will have in this case minus 2 plus minus, and this infinity will be negative value root, so we have I infinity. What do we get? Minus 2 plus minus I infinity. So this becomes a complex number, meaning that what it tells you that this is minus 2 here, right? So write this one. It tells you if you go to, so let's write it here. Okay, so s infinity, k tends to infinity means s equal to minus 2 plus minus root 1 minus infinity, and that minus 2 plus minus root minus infinity is equal to minus 2 plus minus I root infinity, or simply infinity. Okay, so what it tells you that the value will be somewhere somewhere here. So it will go something, it will be here and here. So this is k tends to infinity will be somewhere in infinity, right? So k equal to infinity like this. So this is which point? Minus 2 point. So that means at k tends to infinity, we have s equal to minus 2, in this case is minus I infinity, and when here also there will be a point, and here also there will be a point where will be s equal to minus 2 plus I infinity. So it will have a complex root. Yeah, so that means depending on the value of k, we will find that this may also will become like second order system, which is which will be to start with this will be overdamped system. As the k you increase, this becomes underdamped system. So that's what it's telling you. Yes, because this is in a complex, purely complex root it becomes. Yeah. Okay, so this and how it goes, that we have to find out. Okay, and how do you find out? We find out from here. So what the value is? S equal to minus 2 plus minus root 1 minus k. What you know is when k equal to 0. Okay, so k equal to 1, s equal to minus 2. Yeah. What you see is this actually progresses from here. It goes from here to here. So it comes from here to here, from both the sides. But from this point, it will start going this way. Yeah. So this will start going this way. Okay. So as k equal to 1, this will come to this point. At that, then when k is more than 1, then the root becomes complex, and then you can see here how it started becoming complex. It will go like this. So this is what the root locus will come from here to here, and from here this is going to branch out. Okay, it will go towards the complex infinity, and here also this will go the imaginary infinity. Yes, so imaginary infinity, what I meant. Okay, so the root locus will be like this one. So goes from here to here, from here to here, from here branching out, going to infinity. Yeah. Okay. This way it will be getting more complex and complex and complex. Yeah. So, but here the idea is open loop transfer function can be written as simply there will be a constant k or gain, and then there will be two numerator polynomial divided by the denominator polynomial. Any open loop transfer function may have a gain k, which is a variable, and that may coming from your proportional control that you have put, for example, or feedback loop. The feedback transfer function may have some gain. So this gain is very important because this gain can control many things. Yeah, so hence the idea here is to how to change the gain. Just controlling the gain is going to control a lot of things. What you see here, that if k equal to 0, it is overdamped system. Yeah, so you have here both the roots are real in this case. What you are plotting as a function of k is the roots of the characteristic equation of the closed loop system. So these and these points are overdamped system here and here. And then suddenly you have this point, and this point, just this point is also overdamped. This point where both the roots becomes the same is critically damped system, and rest here or here is underdamped system, because it has complex root. See, this k is so crucial. This k, depending on what you have chosen, k equal to 1, it makes it critically damped. What? K equal to 1. Overdamped, k equal to 0. Underdamped, say k greater than 1. Yeah. So similarly, the zeta will change as you go up and up. Yeah. So as you go up, zeta will reduce. Okay. So I may ask this in quiz or the assignment. Okay. Let's take one more example, and the open loop transfer function is in this case k times s plus 2 divided by s square plus 1. Okay, so this will have a complex root. Yeah, but we also have zeros here, so little bit different from other problems. Okay, so 1 plus the characteristic equation 1 plus t naught s will be equal to k 1 plus k s plus 2 s square plus 1 equal to 0, and hence you get s square plus 1 plus k s plus 2 equal to 0, and s square plus ks plus 1 plus 2k equal to 0. So this is the equation, and from here we can find out the roots, yeah, and what we get, s equal to minus k plus minus root k square minus 4, okay, AC, so 1 plus 2k, like this one, over 2, okay, is equal to minus k plus minus root, and here we get k square minus 4 minus 8k, k square minus 4 minus 8k over 2 is equal to minus k plus minus root k square minus 8k minus 4, okay. We can also write this one is plus 4, let's make it plus 4 minus 8, yeah, sorry, so let it be like this one only, we will see later on if we need anything. So minus 4 divided by 2, so okay, so we write further minus k plus minus k, we are taking this out, and we get 1 minus 8 over k minus 4 by k square divided by 2, yeah, s is equal to like this one. Okay, so now we will use this one when k equal to 0. Yeah, so when k equal to 0, what do we get? We get s equal to 0 plus minus 0 0, so we get plus minus minus 4 over 2, and we get plus minus I simply, okay. So and we expect that just simply making these open loop transfer functions denominator equal to 0, also we can get the same value, and hence we just write it here. So we have this crosses here which corresponds to k equal to 0, so this is minus I, this is plus I, and this corresponds to k equal to 0, right? So this is k equal to 0, both of them. Okay, and next is k equal to infinity, right? K tend to infinity we can use here, yeah. So we can write s equal to minus k plus minus k, and when k tends to infinity, so this becomes 0, this becomes 0, so we have plus minus k only in this case, sorry, plus minus k divided by 2, and what do we get? We get minus k plus k divided by 2 or minus, so we get is equal to either 0 or we get 0 or we get k minus k 0 or minus k, yeah, or 0 or minus infinity. Okay, so what is the meaning of that? Although we have found out the value of 0 minus infinity, but we have to be careful because in limits like this one, which involves you know, the values which will have a k square term is also there, k term is also there, not necessarily what we are getting is correct. Look at this one. For example, if you put this characteristic equation here, this one, we can also write it as this as s square plus 1 divided by k plus s plus 2 equal to 0. Right? The given k is greater than 1, and from there we get s equal to minus 2, which corresponds to k tends to infinity. So this is for sure, because we have seen that this is actually the zero point, right? So we have a 0 point here somewhere, and the value of this is minus 2, right? So we have this here, the value of k is infinity, so we just write down infinity. So the k is infinity. Other this one, we have to find out. We have to find out whether really s value can be 0. Let us say we need to test whether s equal to 0 is on the root locus or not. Any point we did something like this one, we may be making mistake, or how do we test whether we are making mistake here? Yeah, if let us say the s equal to 0 we are finding, s equal to minus infinity we are finding. In this situation, can we test whether really s equal to 0 is really possible, or s equal to minus infinity is really possible? Yeah, that we will find out. From this, it looks like plotting this one is tricky, little bit difficult than what we thought, and hence we have to now use some advanced method, or we have to go to the basics now. Yeah, what is the meaning of that? What are we plotting, and how do you find out, how to really find out some point is on the root locus or not? Yeah, and only when we know that we will be able to plot this one. So we will do it. Let's check, for example, let's check whether s equal to 0 is on the root locus or not. And how are we going to do it? Okay, so let's so we have this equation, right? This is the characteristic equation. This is the equation of the root locus, simply, right? So this is equation of the root locus. Root locus where s can be a complex number. S can be a complex number. Okay, so this is the 1 plus k s plus 2 divided by s square plus 1 equal to 0 is the equation of the root locus. So check if s equal to 0 on the root locus. How do we do? Put s equal to 0 there. So we put 1 plus k 0 plus 2 divided by 0 plus 1 equal to 0. That makes it 1 plus 2k equal to 0, and hence makes it k equal to minus 1 over 2. Now we started with, since k greater than 0, this is not possible, and hence s equal to 0 is not on the root locus. Okay, so what we had got, this one is not true. That means we made some mistake, or maybe this. So let's check whether s equal to 0 and minus infinity are on the root locus. Okay, so check if. Okay, so how to do it? What is the equation of the root locus? So equation of the root locus is equation of the root locus is 1 plus k s plus 2 s square plus 1 equal to 0. This is the equation of the root locus, where k varies. What you have to do? Vary k, plot s. Yeah. So what you do? Vary k and plot s is what the root locus is. Yeah. Okay. Now we can check whether s equal to 0 is on the root locus or not. So s equal to 0. Put it here. So we get 1 plus k 0 plus 2 over 0 square plus 1 equal to 0, and we can find out the value of k. So 1 plus 2k equal to 0, and hence we get k equal to minus 1 over 2. Right? But we started since k is greater than 0, this is not possible. Hence, s equal to 0, not on the root locus. Okay. So whenever in doubt, you made some mistake or because of any reason, if you have a doubt, you can just check whether that is on the root locus or not. Similarly, we can do s equal to infinity minus infinity. We want to check that whether that's on the root locus or not. What we will do? 1 plus k, we can find out k first. So k will be equal to minus s square plus 1 over s plus 2. Now limit, if we have s tend to minus infinity, okay, so k is equal to minus, we put infinity square plus 1 divided by minus infinity plus 2, hence it becomes minus infinity square divided by minus infinity, hence it becomes plus infinity. So basically k equal to positive number and infinity is allowed. So what we see is s equal to minus infinity is on the root locus. So what we find here is we can also find out whether k equal to the s equal to minus 2 is on the root locus or not. You can find out this point s equal to minus 1 is on the root locus or not. Yeah. So s equal to minus 2, if you put here, this becomes 0, and the whole things, in that case k has to be you can write it in this way. See here, if you want to check if s equal to minus 2 is on the infinity, the s equal to minus 2 is on the root locus, what do? You write k in terms of this, so k becomes k equal to minus s square plus 1 divided by s plus 2, and then we have s equal to minus 2, put it here, k becomes minus, and here we have s square, so becomes 4 plus 1, and here we have minus 0. Yeah. So 0, this could be plus minus both basically, because we may approach depending upon which side we are approaching. Yeah. So if we are approaching from this side, for example, if you are approaching from this side, then we will have negative sign. If you are approaching from this side, there will be positive sign. Okay, so let us say we have s equal to like s equal to -2 plus epsilon. Okay, where epsilon is positive. Yeah, if you have positive number, then what do we get? We get -2 plus epsilon plus 2, we get epsilon here. Yeah, and then this is a negative number, hence not possible. So s equal to -2 plus 2, this portion here will not, this one from, you can find out from there that this portion not on root locus. Yeah, why? Because -2 plus any value if you put there will make this term positive, and here we have the negative term, so k becomes less than 0, hence it's not possible. So this whole reason is not possible. This has to be like that. So if you have k, if you have s equal to -2 minus epsilon, and then you put it here, what you get? -4 plus 1 divided by minus this, and this you get 5 over epsilon. And this value is positive, hence it is possible, but that will only happen when you have s more than the magnitude more than 2 or s less than -2, that is -2, -3, -4, all those things are possible. So this also tells you that the value this side are on the root locus. So on the root locus, but this part is not on the root locus. Yeah, so at least we just looking at checking it, you can find out that this is a root locus, this of course on the root locus, this point will be this, but still there is a missing link. Still we don't know exactly how it looks like. Yeah, so we are just some point, just by checking it looks like it's there, but we have to actually find out the complete picture. So what we find so far, that 1 plus k s plus 2 divided by s square plus 1 equal to 0 is the equation of the root locus. Only problem is that s is a complex number. So s is a complex number. S a complex number. So this is a little bit unusual, meaning that we cannot just solve equations and plot it. Well, we can do that. However, we can utilize the property it has. This is a complex number, and whenever there is a complex number, some equation involving complex number, we can have either, we can write in terms of real numbers, the real part and imaginary part, we separate them out, and hence you have two equations, both having the real numbers only now, so it becomes easier, you can solve them, it becomes algebra now. Or we can also, in this case, will work differently, meaning that we are actually getting into the property and the big picture of the root locus, and the big picture is that when 1 plus k s is a complex number, s plus 2 divided by s square plus 1 is there, then we can write like this: k s plus 2 divided by s square plus 1 equal to -1. Yeah, and since this is a complex, left side is complex number, we can apply two things. First, we take the magnitude. So we put k s plus 2 divided by s square plus 1 is equal to magnitude of minus 1 and hence equal to 1. So we get this one. And second thing is the angle, basically, right? So angle phi, so the angle of this, angle of k is plus 2 over s square plus 1 is equal to angle of minus 1. So angle of minus 1 is nothing but 180 degree. Yeah, because this will, in the complex plane, then you have minus 1, meaning that look at this one. Yeah, so we start here in this point, we start from 0. If you start from here, yeah, from this to origin, if you go horizontal direction, positive x direction, opposite the real axis direction, so you have 0, here you have 90 degree, here you have 180 degree, and here is 270 degree, right? So minus 1, if you have a complex number which has minus 1, you write like this one, so like this one, right? So you have a phi here, and then you have some value here. So let us say this is this one is x, this is y, and hence you write a complex number, some z equal to x plus iy, and this is the phi you are talking about, right? So the angle of z we are talking about is actually phi we are talking about. Yeah, and this angle of z we are talking about phi. So basically this phi is nothing but equal to tan inverse, and you have y over x. So whatever the y is divided by x is tan inverse y over x is the one we are talking about. Yeah, so when angle of minus 1 as a complex number, how will you write? We write z equal to minus 1 plus I0. That's why we write. And hence angle of this z, right? So angle of this z is equal to tan inverse y over, so tan inverse 0 over minus 1. Yeah, so this actually corresponds to 180 degree. Yeah. Okay, so 180 degrees. So we have two things in now. What we have done, we have converted a complex equation into two real equations. Now we will have here the only magnitude part. We can put in this case s equal to sigma plus I omega, and finally since we are taking the magnitude, automatically sigma square and omega square will be terms will be there, or sigma. So all other terms, the I term will not be there, or imaginary term will not be there. Similarly here we are changing everything into angle, and by that we can solve. This also gives us some clue basically how it should look like. Yeah, so this is what we will start from this one. Okay, so we have the equation of the root locus we know, but we are now dividing into two parts. One looking at the magnitude, second we are looking at the angle. From there we will solve it. Okay, and solve it how? Of course the root locus method we are studying, that is a graphical method. So we will just construct it, just looking at this one, and we will construct the root locus for this open loop transfer function. Okay, so that is all for today.